So the work I'm going to talk about today was done with Woei-Nan Bair, Sung-Jae Hwang, Jane Clark, and John Jeka at the University of Maryland. And it concerns how the nervous system activates muscles at multiple joints in order to stabilize upright stance. And it does so by using sensory information, as we just saw, from proprioception, vision, and the vestibular system. And everything today will be the sagittal plane. And I'm going to use a two-joint ankle and hip model of the body. And the question is, how does the nervous system use sensory information to specify muscle activation to stabilize upright stance? And our approach is to use what's called closed-loop system identification. This was originally used for standing posture by Fitzpatrick back in 1996, and more recently by other researchers such as Van der Kooi. And there's two parts of this. There's identifying feedback, which we define as the mapping from body sway to muscle activation. And defining that way, feedback, when I just say feedback, that includes all of the sensory modalities. And you can also identify the effect of specific sensory perturbations, for example, vision. And I'm going to assume this following linear model where you see we have a plant, which consists of muscles, tendons in the body, and we have neural feedback, which includes sensory systems and the neural controller. I'm going to assume that sway, which is kinematics, has three sources. Sway is produced by muscle activation as measured by EMG, and that's described by a plant P of F. If there's mechanical perturbations in the experiment, that affects sway, and that's defined by an open loop effect transfer function. I should have said that these equations are in the frequency domain. So the open loop effect of mechanical perturbations is described by a frequency response function M of F, and there's noise. In the same way, EMG has three components. EMG is affected by sway via feedback big F of F. There's an open loop effect of any sensory perturbations that are present, which is described by big S of F, and there's noise. So these linear equations in the frequency domain will be the basis for identifying the system. So I'm going to talk about two experiments. The first experiment is actually a developmental study. There were three groups of subjects, 6-year-old children, as pictured here, 10-year-old children, and young adults. And there was one sensory perturbation, which was rotation of a virtual visual scene about the axis through the subject's ankles. And there were two mechanical perturbations. So there's these weak springs that are attached at one end of the subject. At the other end, you can barely see them, are linear motors. So their perturbation signal is the position of those two motors. So we have these three perturbation signals. One sensory perturbation, V of T, which is a visual scene angle. Two mechanical perturbations, and those are independent white noise signals with power from 0 to 5 hertz. And there's two conditions. There's a low amplitude and a high amplitude condition of the visual motion, and they differ by a factor of 2 in amplitude. So this shows what the signals look like in this experiment. This is 10 seconds from a trial, and the trials are either 2 minutes long or 4 minutes long, depending on the age of the subject. 6-year-olds cannot stand for 4 minutes. The first signal shows the visual scene angle, and the next two signals show the waist motor mechanical perturbation and the shoulder motor mechanical perturbation. And then we have what we call the weighted ankle EMG signal. What we do is we take rectified EMG signals from ankle muscles. If it's a posterior muscle, we give it a positive weight. If it's an anterior muscle, we give it a negative weight. And we adjust those weights to maximize coherence with the three perturbations. So that gives us the weighted ankle EMG signal. And then in the same way, we take hip muscles and we create a weighted hip EMG signal. So those two signals are the inputs to the plant, and the muscle activation signals. And then we have the two kinematic variables, leg angle and trunk angle, in the sagittal plane. So we have two kinematic variables and two EMG signals. So how do you identify feedback? You use mechanical perturbations to identify feedback. So everything I'm going to show you, the left-hand side will always be gain as a function of frequency, where gain and frequency are both on a log scale. Frequency goes over roughly 2 orders of magnitude from about 0.04 hertz up to about 4 hertz. And the right-hand side will always be phase. Frequency, again, will be on the horizontal axis on a log scale. Phase will be in degrees. The first row shows the closed loop response to mechanical perturbations on EMG. So we had 2 mechanical perturbations, 2 EMG signals. So that's a 2 input, 2 output closed loop frequency response function. So it has 4 components as shown there. The second row is the closed loop response of the kinematic variables, the lag angle and the trunk angle, to the same perturbations. And the point is, if you try to interpret the first 2 rows, it will be very difficult, because those responses depend on the plant, they depend on feedback, and they depend on specific properties of mechanical perturbations. But if you go back and you look at what we assume about EMG, what you find is that feedback maps the kinematic responses to mechanical perturbations to EMG responses to mechanical perturbations. So if you can solve for feedback by taking the EMG response times the inverse of the kinematic response, which is shown on the last row, and that's feedback. So at this point, you get something which is relatively easy to interpret. So in the previous study, we showed that this feedback looks roughly like optimal feedback, in which you mainly try to minimize muscle activation. So you can see it looks kind of like PD control. At low frequencies, you have a plateau and then gain goes up. Phase is initially near 0 and then it goes up. Eventually it has to go down because of time delay. I should say that this data is from the 6-year-olds. Unless otherwise stated, I'll be showing you data from that group. So that was feedback, which depends on all 3 modalities, or all the modalities that are present. So how do you identify, for example, the open loop effect of a visual perturbation? So the top row shows the EMG responses to the visual perturbation. So now we have 1 input, which is the visual perturbation, and 2 EMG signals. So you have 2 components to that frequency response function. Second row shows the kinematic response to the same visual perturbation. You go back to the equation for EMG, and what you see is that the closed loop response of EMG to the visual perturbation depends on feedback times the closed loop kinematic response plus this open loop effect of the perturbation, which is what we want. So we can easily solve for S, and that is shown in the last row. So that's the open loop effect of vision on EMG. It does not include the plant. It's the direct effect of perturbing vision. And the point is, this is something you can think about. So there's 2 things you can look at. For example, you can compare the closed loop response to vision to what we just identified, which is the open loop response to vision. So closed symbols, red, are the closed loop responses to vision, and the open symbols, blue, are the open loop responses to vision. And what you see is that high frequencies, they coincide. And why is that? If you actually write the closed loop response, what you get is, it's actually 1, the identity times minus f times p times the closed loop response to EMG. So at high frequencies, f times p is typically small, because there's more low-pass filtering in the plant than there is high-pass filtering in feedback. So at high frequencies, the closed loop response is almost the same as the open loop response. The other thing you can look at is how does visual feedback compare to overall feedback. So here, red is the overall feedback you would expect if you rotate at everything, all your references about the angles. In other words, it's what you would expect if the human only relied on vision, is the red. The open symbols are what we just identified as the visual effect of the perturbation. So the first thing you can see is that vision only accounts for a small percentage of feedback. It's about 10% in this example. You look at phase, and you can see that at low frequencies, the phase of overall feedback and visual feedback is roughly the same. But at high frequencies, visual feedback has a much larger phase lag than total feedback. And the reason is vision has a longer time delay than these other modalities. So you can basically see from this that vision has a constraint that makes it less useful at high frequencies. So one conclusion is that visual feedback is not a scaled version of total feedback, because vision has different properties from the other modalities. So you don't want to just use it in the same way you would use proprioception, for example. So now let's go to the effect of visual motion amplitude on this open loop effect of vision. The top row shows this identified open loop effect of vision for the low amplitude condition. The middle row shows this identified open loop effect of vision for high amplitude, and the last row compares them. So, for example, this is the gain ratio. And you can see that at high frequencies, the gain in the high amplitude condition is less than the gain in the low amplitude condition, which is what you expect. As vision motion increases, you want to rely on vision less, so the gain goes down. And what you see is that this decrease is similar for both the ankle and the hip E and G signals. So this is one way of using this system identification approach to quantify reweighting of different senses as conditions change. But are you sure that this really is sensor reweighting? Because what we've identified is actually the open loop response from the sensory perturbation vision to the control signals U of T. But that also depends on, for example, the control strategy. So I claim that what we just saw was a reflection of adaptive state estimation. So one way of checking that is to look at overall feedback for the two amplitudes. So the top row shows overall feedback for the low amplitude condition. The bottom row shows overall feedback for the high amplitude condition. And you can see they're roughly the same. What that means is that as you change your weight to vision, for example, if you downweight vision when visual motion increases, you're going to upweight something else to compensate. For overall feedback, it does not depend to any large extent to the sensory condition. Now, that's not what you would expect if the control strategy is changing. If the control strategy changes, you would expect overall feedback to change. So this suggests or strongly indicates that it's not the control strategy that's changing, it's actually reweighting of different senses that have changed. So this is the conclusion, that the decrease in gain that you see here when you increase visual motion amplitude is primarily the effect of downweighting vision. It's not a change in the control strategy. If you look at, so that was 6-year-olds. If you look at young adults, you see something similar, perhaps a somewhat larger decrease in the visual weight. So perhaps there's a developmental effect where the ability to adaptively reweight different senses improves as you mature during childhood. And this is the second experiment, which is just young adults. Now there's two sensory perturbations. The second one is not relevant to this question of the open loop effect of vision. But there was also an Achilles tendon vibration. But now we have two surface conditions. We have subject standing on a normal flat surface, and we have subject standing on a beam whose width in the anterior-posterior direction is 50% of the length of their feet. And what do you see? If you do the same analysis and you look at the open loop effect of vision under these two conditions, and you compare gain in the short surface condition divided by gain in the normal surface condition, what you see is that the vision to ankle EMG gain increases. But what's important is that it increases more than the vision to hip EMG. So recall that in the first experiment, both ankle EMG and hip EMG changed roughly the same amount. In these two conditions, what happens is ankle EMG is going to use sensory information more, and it's going to increase a larger percentage in terms of gain than hip EMG. And we refer to this effect as differential sensory reweighting. What that means is reweighting is not the same for all actuators. So you want to use sensory information differently for the ankle than the hip. So in conclusion, closed-loop system identification can reveal the nervous system's mapping from movement to muscle activation, what we call feedback. That's overall feedback. You can also use closed-loop system identification to find the effect of a sensory perturbation. For example, what information does it provide? And then you can see how that modality, for example, vision, contributes to feedback. For example, when standing on a short surface, we saw that the nervous system differentially increases the weight of visual information when specifying activation of the ankles compared to the hip muscles. And what interpretation is, when you stand on a short surface, proprioception becomes less reliable. So you're forced to downweight proprioception, and vision takes the place. So that's why you can see differential reweighting between the ankle muscles and the hip muscles, because this condition degrades proprioception selectively at the ankles. Thank you.
We have time for questions. Quick question. You mentioned time delays, and can you give me an idea, just in seconds, what the time delays are like for vision versus proprioception, and why would there be a difference?
Vision is about 250 milliseconds.
That long?
Yeah. And proprioception is maybe 100 milliseconds. I see some agreement. That's good. So vision is the slowest sense. I think vestibular is in between proprioception. I mean, it depends on which, exactly what type of proprioception you're talking about. But vision is the slowest. So that's what you see. You see that there's a time delay associated with vision that's different than everything else, and that implies that the nervous system should treat vision differently.
Do you know or care whether the spring force is being sensed in the skin or the ankle joint or in the hip joint or in the pressure on the lungs? Or does it matter to you?
Yes, we care very much because the method depends on the mechanical perturbation producing movement, which is then detected by the nervous system. That's kind of the definition of a mechanical perturbation. Something that first produces movement, and that movement is detected by the nervous system. If you directly sense the perturbation itself, then it's not a mechanical perturbation the way that we defined it. Now, as a subject, people get used to this very quickly. The other advantage, I think, is that it's not a natural perturbation. For example, you may be used to using shear forces on the foot to give information, but people are not used to using, springs tugged gently, and these are very gentle perturbations, as a way to control posture. So our hope is that its effect is through movement, not any direct effect.
The short beam on the foot and the ankle vibrators were to eliminate reactive force sensing?
No, the short beam So the question was, what was the purpose of the short beam and the vibration? So the short beam was to create these two situations. And actually, the interesting thing about the short beam is it can affect everything, right? The short beam can, in principle, affect the plant. I didn't show you the plant. We also identified the plant. And it showed some effects from the short beam. But our method lets us separate the reweighting effects of the short beam from the mechanical effects of the short beam. So the short beam was to create this new condition in which a subject may adapt a new reweighting, they may adopt a new control strategy, and our goal is to pull apart those different effects. So we have the plant may change, feedback may change, and the reweighting of vision may change. And our method allows us to measure each of those three things separately. Now, vibration was the second sensory perturbation, which along with vision allowed us to identify the plant, which I didn't show in this talk, but we also used the two sensory perturbations to identify the plant.
So two things. One is I'd like to fill in just a little bit of information about the visual system. So what Tim is talking about is that the reason why vision is so slow is because you have a bunch of different processing steps, which more processing than occurs with the other sensors. So vision, you have processing of the retina, and then it goes through a ganglia, and then goes to the visual cortex, and then it goes to the brainstem where presumably this is happening. So all those layers are costing you time. And then I have a question, which is, I'm not sure if I can really interpret this as sensory reweighting in the case of the short beam, because it seems like I should just choose a different feedback controller, and even if I didn't have a sensor at the ankle, and let's say I was using a state estimator to construct the ankle, I would still have I would expect a lower feedback gain on the information about the ankle states, as opposed to necessarily the sensory information from the ankle.
I mean, that's certainly plausible. I didn't show it, but we identified the feedback, which had no obvious change, overall feedback, which suggests the control strategy is not changing. And we identified the plant, which also had some change.
But haven't people claimed that on a beam that you use less ankle torque?
People have claimed that, and this experiment was designed to test exactly what the difference is between standing on a normal surface and a beam. Because the problem is, because you're on a beam, things change. I mean, the closed loop response in kinematics will be different to a visual perturbation will be different, and other things will be different. The question is, what causes those differences? Sensory reweighting, when you differentially reweight ankle and hip, introduce changes that may be interpreted as changes in the control strategy, but you have to test the different alternatives. So we have a plant, we have a feedback, and we have the direct effect of vision, and we can look at each of those three and see what is actually changing.
Okay, but if you were standing on a rod, super short beam, then wouldn't you expect the feedback gain to change? Because you have to use a different strategy.
Yeah, no, at some point the feedback strategy would change. We just didn't detect it with a 50% gain, but we did detect other changes.
We got time. We're good. All right, let's thank our speaker.